Class is now starting. All attendees are in listen-only mode.
Well, good afternoon or good morning to everyone. I hope that you can hear me. Welcome to the weeks 3-4 S2S webinar series. And as many excuse me, as many of you are already aware, this monthly series, co-sponsor between the OAR Weather Program Office S2S program and the Weather Service OSTI modeling program. And I'm Mark Olson from the WPO S2S program. So we have a good talk today by Eugene Xu. But before we begin, I wanted to remind everyone of the webinar series website. And I'll post the address in the chat box shortly. But on the site, you can see information on the upcoming talks, and you can add yourself to mailing list. And you can also access recordings of past talks. And also, I really do want to highlight there's a form available if you're interested in presenting in a future webinar and spreading knowledge of your work. We currently have some spots available over the next few months, so encourage you to consider giving a presentation and kind of expose your work and possibly spark some discussion, collaboration, and all of that, and let people know what you're working on. Finally, if you have questions for the speakers today, or for the speaker today, we only have one, during the presentation, please post them in the discussion document, and it should be posted. There's a link in the chat box of the webinar interface there. And I'll periodically post the link there as well. But so you can go ahead and join that and post your questions in there for the speaker. And today, like I said, we only have one speaker, Eugene Xu from NOAA's EMC. Is going to be talking about development of the UFS coupled GEFS for weather and subseasonal forecasts. I'm going to go ahead and get started and switch it over to Eugene to be presenter here, and let him take it away. There, we can see your screen, Eugene.
See my screen, right?
Yep.
So let me close this one and my slideshow. So see my full screen?
Yep, it looks good.
Okay, everyone. Good afternoon and good morning if anybody from West Coast. Okay, yeah. Much appreciate the WPO, Mark and Christine to invite me to talking about this subject, development of the UFS coupled GEFS for the weather and the subseasonal forecast. My colleague from EMC have a name over there, and also the Phil from PSL and Professor Liang and Dr. Xin from UCMerit. And also like the acknowledgement to the EMC coupling and the model group, CPCs and WPO CTP project. So my talk for this talk, mainly have a few components, the introductions, and give you some background of the GEFS SubX system and GEFS version 12 and the reforecast already in operational, and experience mainly the UFS coupled with the GEFS configurations and test different horizontal resolutions and tune the stochastic. That give you a summary. So if you have a question, the couple options. One is you put it in the chat, the QA section, or if you have immediate question, you can, I can see, I use my full screen. You can in the chat or talk in I don't know, the Mark can control that one. Yeah. And in collaboration with the UFS, R2O, and S2S, and also the media range weather applications, we are focused on to improve the NSAP GEFS for the subseasonal prediction from a current operational. Mainly for this talk is based on the CTB funding the project for the past 2 years. It's a project that just ended by the July 31st, I think, officially. Yeah. The GEFS version 12 was implemented in NSAP operational September 2020, which is the first UFS application with copper to wave watch 3 ensembles with 31 members and about 25 kilometer horizontal resolution, out to 35 days to cover subseasonal prediction. That's first time for global ensembles. And we are in several places already demonstrated that operational GEFS have a very good capability and excellent performance for subseasonal time scale, include MJO predictions, surface temperature, and precipitation through 31-year reforecast before it was implemented. Yeah. For this work, we are mainly focused on the coupling system, and also for talking about ensembles, we are talking about quantify forecast uncertainty is our main work. Due to the model is significant change from atmosphere only to couple with the ocean, sea ice, and others. So we need to see what is the performance, basic performance, without the big tune or adjustment. So this talk is mainly based on the UFS, the prototype 5, P5. I guess most of you are aware of that one. That's the virtual MC leading the the UFS prototype from P1 to P8, currently running P8 now. Yeah, our experience based on a 2-year period. Yeah, the initialized once per week, only the 11 members, 10 perturber and 1 unperturbed members, out to 35 days. We have 4 evaluations, but today we can pick out the highlights to tell you what it look like from different resolution and the P5 based ensembles. Yeah. And before that one, I give you a couple of the slides talking, that we call the background. Okay. So NSAP the GEFS usually running out to 16 days to cover weather and the week 2 forecast to support the CPC as well. Yeah. However, before that one, the WPO, the support of the CTB, the found us to extend the GEFS to 35 days to support the SubX. That's called the NOAA CTB Subseasonal Experiment, SubX. Okay. So before that one, the GEFS ensemble, the MJO, the capability is pretty lower. See over here is the black curve. Since SubX, we are trying to enhance improvement of the subseasonal prediction to focus on MJO as a main target. So we did several improvement, the stochastics and the traffic convection to corresponding by the GFS models, and also the service. Since we are not coupling with the 2-tier SST at that time, so each the process to enhance the MJO scale based on these 2 years. See, from original 13 days, the SubX version will contribute to the community about 22 days. the green line over here. In the same period, we compare with the CFL version 2. I think the skill is better than the yellow one, the CFS version 2. The interesting people could be review the several articles. One is the BOMs, the review the SubX, overall, and also we have our own publication, the 1 or 2 list over here. Okay. And for current operational GEFS version 12, based on the reforecast, we also studied the model capability for the MGO. Here, demonstrate the one called the OAR anomaly and the zonal mean, F50 zonal mean anomaly. So here is the color show the OAR anomaly, the time lag, the correlation center at the center of the Indian Ocean. And the left panel showed the observation, and the right panel showed the GEFS version 12 reforecast lead time 30 days. I can see that not that perfect, but you can see up to 30 days, we still see the MGO eastward propagation. We can catch up the OAR and also zonal wind. So that work also showed certain papers we list over here. The interested people can review our papers for the current operational, the GEFS, and the reforecast. And GEFS version 12 was in NSF operational since September 23rd, 2020. 31 members of 35 days with the 31-year ensemble reforecast to support a stakeholder the calibration for the subseasonal forecast. And at the real time, at that time for implementation, the NOAA website also announced the NOAA upgraded global ensemble forecasting system. Yeah, I think it's a big achievement in the past years. Yeah. And start talking about the currently we are running the coupling ensembles. Okay. So the first one, talking about configuration of the UFS coupled with GFS. We are experimenting the period of about 2 years, the October of 2017 and September 2019. And we use the GEFS version 12 reforecast as benchmark or reference or compared to, okay. The reforecast is same configuration as the current operational. Yeah. With the new stochastics, the SKEB and the SPPT 5 scales, the coefficients set up over here. And we are using the P5 coupling the configuration. We're running the 2 sets. One is we call low resolution. That is a half degree for atmosphere and ocean and sea ice, and also high resolution. High resolution is the quarter degree, the same as the reforecast resolution, but the coupling, yeah, it's coupling. So we also adjust the coefficient of the stochastic SKEB from 0.6 to 0.7, and 5 scale the SPPT will reduce proportionally like 30%, because we detected some traffic still the over dispersion. We do this kind of adjustment. Yeah, it's our challenge. I'm a speak ahead. We have a limited the quality of initial conditions, and no cycling, no dynamic fields for the oceans. So this evaluation is more to focus on the extended range. For the short range, definitely the initial condition will play the very important role. Yeah. Okay, so I'm also block over here. That's called the ensemble prototype 1. We also designed the ensemble prototype 2 that based on the P7. and ensemble prototype 3 based on the P8. Yeah, so that's we are talking about that later. Yeah, the SPPT and the SKEB, the two the new implement stochastic schemes, and the SKEB the mainly we call the dynamic the stochastic. Okay, it's kind of the stochastic kinetic energy, the backscatter. For our models, the SKEB, the function, mainly take on the model dissipation, dissipation, the highly depend on our the numerical scheme, like the diffusion. For example, horizontal diffusion. If the diffusion order is higher, you have a less dissipation. The SKEB function gets smaller or less. If the diffusion order is lower, your truncate or damping very strong, so dissipation will be larger. So SKEB contribution will be larger. Yeah. SPPT is a physical tendency perturbations that use very popular by many the numerical models ensembles. Okay. So we are use the 5 different scales, spatial and temporal scales. The show over here, the diagram, the total combined these 5 scales as the first one. The final coefficient is about the 0.95. Yeah. So I give you the quick examples on the right. The 11, we also have stochastic, but the very limited the contributions. We call the STTP, stochastic total tendency perturbation. We are upgrade every 6 hours. It's a very limited contribution. So we still see the much under dispersion and over dispersions in some area. After we use the new stochastic, you see right at the bottom, it's much better. This is the ratio. The color is light, the better. Yeah. Okay. So the experiments we are running the coupling. We call the high resolution and the low resolution. High resolution is a quarter degree and the low resolution is a half degree. Yeah. So compare with the reforecast. Here is a 2-year average. For the northern hemisphere, the 500 geopotential high. The left one is CIPS, measure the ensemble distribution. Yeah. So the similar, the CIPS score itself is similar as the PSC, but the measure the probabilistic. Right is the PSC, the pattern anomaly correlation. You can see both the low resolution, high resolution have improved scale compared with the black curve. For the short range, the week 2, and the subseasonal, all the way you can see the better. Both the ensemble mean, right one, and the distributions. Yeah, that's good. And see, next one, we have a summary tables for this 500 geopotential high for the week 1, week 2, week 3, week 4 for each domain, the northern hemisphere, southern hemisphere, PNA domain, and the tropical. We also did the significant test. Particular, you'll see the week 2, we are significantly better than the current operational. And southern hemisphere, also the tropical, you see the star means the significantly better. Only I want to say over here, if you see the week 2, the northern hemisphere have better scales. It mainly happens for the low resolution. It's slightly, the high resolution also better, but the low resolution is best. Around this 3, yeah, is significantly better than the current operation. What does that indicate? That indicates, for extended range, it may indicate the resolution may not play the very important role. Yeah, but talking about the ocean model is a different story. Okay, yeah. And look at the low level, high level zone wind around the each domain. Top 3 is the A50, that's low level, northern hemisphere, southern hemisphere, and tropical. And the bottom is the 250 for the northern hemisphere, southern hemisphere, and the tropical. 3 curve here is the same as the reforecast, the coupling ensemble, low resolution, high resolution. We not see much difference from the both hemisphere, but the tropical have a significant difference. For the low level, particularly, you see the ensemble spread. Ensemble spread for the current operational is over dispersion. It's much larger than the Rubin square errors. And both high and low resolutions reduce the spread. And also, if you see the green line, also a little bit reduce the errors. Okay, we call the improve, yeah. And 250 also similar, the little bit less than the F50. F50 is more typical, yeah. And for the precipitation, we also evaluate, see the bias, the week 4, I'm sure over here. For the week 1, week 2, we also have the result. It's very similar. I put a week 3, week 4 over here. Want to see what is the longer lead time we impacted by this coupling. For the P5, since we are not running any cycling DA or weekly DAs, we still using the GFS version 15 retrospective the analysis, and we saw some degradation in terms of bias and RPSS for both lower, high resolution. The low resolution degrade a little bit larger, and the high resolution still a little bit degrade. And also, we make the significant test not in a significant level. Okay, I think mainly this one may conclude from the cycling. If we have the same system cycling, we may get better of this kind of performance. Okay, and 2-meter temperature. 2-meter temperature, the week 1, week 2, no, week 1 and week 3, week 4 on the bottom, week 1 on the top. Okay, the reforecast, low resolution, high resolution, the left, middle, and the right. Okay, I can tell you the 2 characters for based on all the experiments. One is the around the Tibet in Asia. This part, doesn't matter week 1 and week 3, week 4. All the 3 experiments you see is consistently or steady. You see the warm bias. Okay, and another character only happen for the coupling. That is the North America. Okay, you not see much from week 1, but the week 3, week 4, you see the increase the bias. So what I believe that for this Asia, the warm bias. Okay, this part may be due to the model initial analysis. Okay, that keep the steady from the beginning to the end. Is no big change with the lead time. And another part, this one, is growing. You not see the much from beginning, but you see the much increase from. That may be the model handling, the PBL and the land surface, the part. Yeah, both of them we already feedback to the model developer. Yeah, and for the hurricane, the tropic storm, since we're running once per week, the sample is very limited. The sample size, you can see the bottom over here. For the track, the errors is very similar. We see the high resolution reduce the errors, and the spread is much improved, and low resolutions see some degradation for a longer lead time, not see the for a short lead time. The importantly, intensity, we see the much improved for the short lead time for the high resolution. Of course, low resolution intensity is not the favor. It's much degrade. Yeah. And MGO scale. We use standard CPC the method to evaluate the MGO scale. IM2 and the combination. The top, the 3 is the IM total, and IM1 and IM2 three curves here, clearly the reforecast, high resolution and low resolutions. I can see the both high resolution and low resolution have the even or better skills, MU skills for the compared to the kind of operation for all the lead times. See the combination, and only see a little bit over here, around the week 3 time range, some variations over here, and the IM2 is much better. The low resolution also showed much better the performance for the IM2. Yeah, and also we evaluated the Loomis square error and the spread of MGO, the components. Yeah, the combination, and for the kind of operational, it's kind of over dispersion. I said before, yeah, the tropical winds, you see that, and after we adjust the stochastic, you see the both of them reduce it. Yeah, still not optimal, but much better than we reduce the errors and reduce the spread. Yeah, and we also did a lot of the diagnostics to see the spread error ratio. This is a 52 case for 6 days, and this is summer. The high level and the low level. This is the ratio. You see the color bar over here, and the light color is better. Okay, I say before the F50, it's more over dispersion. You see over here. After we adjust, we see some improvement, particularly for F50, it's much improvement. Okay, it's much better. And for the winter, it's very similar, not completely the same, but a very similar behavior. F50, the over dispersion for all this tropical land, particularly, you see the over dispersion. After we are adjusting the stochastics, or particular SPPT, we saw that we much improve it. Okay, yeah, and we also diagnostic, the ensemble variance and ensemble errors using the collinear variance model. That's originally also by the Water Klosky, the PhD works. Yeah, the horizontal, this is also 6 days tropical, the summer on the top and the winter on the bottom. This is the reforecast. This is the coupling, the low resolution. This is high resolution, and the horizontal represent the ensemble, the variance, mean ensemble variance corresponding to the error variance. Ideally, you want to see that the perfect is around the diagonal. However, you cannot achieve that one because first one, we only have 11 members. Ensemble is not sufficient to represent the 4, uncertainties. Okay, so we use that concept to adjust to the dash, the regression line, the dash. That's assuming you have sufficient ensemble size. What does it look like? Based on this kind of diagnostic, you will see the high resolution give the best the options. Yeah, the better than low resolution, better than the reforecast. Okay, and this is a very close section about the ensemble error and the spread ratio. This is a kind of operational or reforecast that we see that we're talking about tropical over dispersion. After adjustment, this over dispersion is much improved for the low resolution and high resolution. Okay, and other component we also look at, like the SST, the downward shortwave radiation flux, and the latent heat, the flux. Okay, so I can give you the quick summary. This global SST, the bias, the coupling, both coupling is much better than the original, the operational GEFS or reforecast. This is a Loomis square error and spread. Loomis square error is very similar, but spread is, increased. That's more natural because the kind of operational we don't have a full coupling, just use the boundary forcing, And Nino 3.4, we also see this small domain, the SST, the coupling is get better and similar performance as the global for the Roomy square error and spread. And we not see much difference from latent heat flux and downward shock wave radiations. And looks to me the Roomy square and the spread ratios itself is pretty comfortable. Not see much. Only see the downward shock radiation, little bit of over dispersion, but we are reducing after coupling. And SST bias, for the coupling, this is the comparison for high resolution and the reforecast or operational, not compared with the low resolution. It's a very similar. I'm, not present for low resolution here. We not see much the difference, okay, for the bias itself. We probably see little bit of the coupling increase the warm bias around the tropical here for the longer lead time, long lead time, and also see some variation of this is the active, the ACC, the area, okay, So here you will see in the next couple of slides have the same the characters, And this is the Roomy square and spread difference for the high resolution and the reforecast. We are not, tropical Indian Ocean, Roomy square and high resolution are reduced for the short lead time, but increase for a longer lead time. I'm presenting over here that we are not tuning the ocean model and the atmosphere model, just running the P5, okay? And the only work we are tuning the stochastic, okay? So this is the behavior. I just straightforward to show you, and the spread on the bottom with the lead time change, the spread increase. That's pretty natural, okay? And the downward shock wave radiation, the bias, compared with the high resolution coupling and the reforecast. Let's focus on the bottom, the day 4, day 18, and day 32 difference, both difference, I'm highlight around the tropical from Indian Ocean to the Pacific, we are overall both the reforecast or operational and the coupling have a warm bias, okay? Warm bias is but get some the improvement for the longer lead time you show over here, And latent heat, also the day 4, day 18, and day 32, the bottom the 3 panels that show the difference from a reforecast and the coupling, So I think we saw the big character around the Northwest Pacific, is a big reduce the bias of the coupling, for this area. And for the tropical domain, we do see some negative, reduce the bias for the Indian Ocean and Maritime Continental and the West Pacific and the tropical Pacific, part. And here is just the previous 3 slides. I put the short downward shock wave radiation and the latent heat and SST bias for the coupling, high resolution coupling, to compare these 3. You can see the SST bias, the increase around Indian Ocean to the West Pacific. See here with the lead time at the beginning, day 4, you don't see much, day 18 and day 32. And for the downward shock wave radiation flux, you not see this character. It's more steady, little bit of increase, And latent heat, and also a little bit, not for, yeah. We are understand over here is SST1 bias increase with lead time over the tropical, and a larger positive bias persists for the same location. A larger positive bias slightly increased with lead time for the same location. Persistent warm effect from downward shoulder radiation bias dominates cooling effect from latent bias. This leads the closing warm bias in SST. Yeah, that's the explanation for this one. And based on this, this highlight, I give you the summary of the coupling ensembles high resolution and low resolution. We call the EP1, ensemble prototype 1. Yeah. So overall, the coupled GEFS, low and high resolution, extended the prediction scale from GEFS version 12 reforecast or current operational GEFS. The coupling the high resolution is better than low resolution for weather prediction. The coupling high resolution has the closest scale for low resolution for extended range, week 2, week 3, 4 forecast. But it indicates the higher model resolution does not take advantage for extended range forecast. I talked about MGO and the week 2, the 500 Japan high scale before, yeah. The forecast uncertainties of coupled GEFS, both low and high resolution, are adjusted very well from updated SPPT and SKEB to enhance probabilistic forecast scale. From a limited case, the tropical storm tracks of the high resolution is slightly better than for the short lead time, and the intensity is much better than low resolution and GEFS version 12 reforecast. MGO scale of coupling system is better than reforecast for all lead time. The high resolution reduced ensemble spread, but still over dispersion, yeah, little bit. The corners precipitation of coupling is slightly degraded than the reforecast, but it is insignificant, yeah. Coupling system introducing a slight warm bias of surface temperature for corners, which could be related to the land model and the PBL schemes. Yeah, the tropical forecast spread may still be larger than error, which result in MGO uncertainties over dispersion or underconfidence. Yeah, I talked that before. We are challenges because we're only able to run the limited ensemble members. For this case, we're running 11 members. It's not sufficient to represent the full uncertainty since we spend a lot of time to evaluate the uncertainties. Okay, so that is one, and also all the model runs, we know the cycling initial conditions just to use the exist whatever variables initial conditions that may degrade or unmatch with the coupling model system for at least for short lead time. Some degradation is pretty natural, okay, personally, yeah. All this work, we construct a manuscript for publication. The process is under review right now. Yeah, this is what I posted for a talk, I'm talked to the Mark since today I'm only one presenter, so I have a bonus time to, so I like to show the informations. It's the same models, P5 basic. We run in the 9 months. I call the answer predictions from the preliminary UFS seasonal forecast system. My coworker, the Bin Fu running the system, and Hong Guan did a lot of the evaluations, and the fear from PSL, Virtual, and the VJ all contribute to this work. So if you don't mind, I'll take about 10 minutes to talk about this is the first time, and also give you the paper to look at what is the capability of the current coupling model system to predict the season prediction. I'm mainly focused on the ENSO prediction at this time, okay? So the configuration, the same configuration, but we run in the lower resolution, yeah, for the seasonal prediction. They run in the C192 and the 64 level, still the P5 basic, and the similar atmosphere model as the GEFS version 15 and the GEFS version 12. We retain the NST to assimilate the SST dyno variability and expect to reduce the code ST bias. Yeah, and the ocean and the CIs, we both run in the half degree to match with the atmosphere. I'm not sure this optimal, I'm just test that one. We are a lot of the additional diagnostic evaluation ongoing to give the future more suggestions, but this run, the atmosphere, ocean, CIs, we run in the half degrees. Yeah, the experiments does not include the waves. Yeah, stochastic is the same setting as I talked before, the seasonal run. The atmosphere, the 5-scale SPPT have 30% off from kind of operational, and a SKEB from 0.6 increase to 0.7 for operational. And the ocean, we also run in the field in storage, called the PBL perturbations, the perturb the total kinetic energy generation and the dissipation. And we call the SPPT styles perturbation perturb the SST, actually the ocean, the temperature and the salinity and a layer of thickness. Yeah, it's a coefficient like this. All the 5 scales is not reduced. We don't know what is the good one. There actually more testing to see, but this is the default operation, the default setting. Yeah, and the initial conditions, we are start from June 1st. For each case, we run in the 3 cases: the neutral case, the 2012, and the El Nino very strong El Nino case, the 2015, and the 2017 La Nina case. Okay, we first think about start from May 1st. However, we have a difficulty to have the complete or match the initial conditions. So we decide to use the June 1st to run in 9 months. The atmosphere, we are in the GFS version 15 retrospective analysis and version 12 reanalysis. And the ocean use the GODAS interpret to the half degree, include the ocean current, the 4 fields, and the ice use the CPC analysis. We're running more members, try to see it will help. We're running 41 members out to 9 months. That means the unperturbed, the 40 unperturbed members. Okay. And here is an El Nino case. This is a very strong El Nino case, and the top plot is all the coupling ensemble with 41 members, and I tried to compare, to pick up the plot from CFS version 2. The difference over here, the CFS version 2 have a bias correction, but our testing, we don't have a bias correction. We don't have enough information to talking about the systematic errors. Okay, so we have 41 members. The CFS also have a legged 40 members, which I tried to get the same start points. Okay, you can compare each other. For the El Nino case, I think the CFS version 2 have a very good predictions. Yeah, this is the observation, and they extend the observations. And the 40 members. Ensembles our ensembles running without bias correction, we are also is very good. That we can predict the answer, the trims, only that we maybe have some bias, and we can talk about that later on. We have the curve here. I can see the red is analysis or observation, and the purple here is a control, ensemble control, and the blue is ensemble mean, and green is ensemble median. We found that a couple of the interesting characters. The one is our the ensemble spread for the Nino 3.4 domain SST is pretty large, way larger than others. Okay, the first one. Second one is a ensemble 41 members here. Distribution is not the normal distribution, not the Gaussian distribution. Always tend to the extreme side. That means the ensemble median is not same as ensemble mean. See, the green is the ensemble median, the blue is the ensemble mean. Okay, let's look at the another case. Is La Nina case. The La Nina case. I need to mention the SST analysis using from a CFS version 2 and ours is slightly different. So you will see the initial time, probably the less than half degree difference, that need to notice, okay? However, you see over this one La Nina case, the red is the observation and the green is the ensemble median. I think the ensemble prediction is pretty good, okay? Not perfect, it's pretty good to simulate the La Nina case. And compared to the CFS version 2, we are, I can say it's slightly better than the CFS version 2. Even they already, the bias correct the SST, okay? Another two characters that I said before is ensemble spread, ST spread is pretty large, still larger. And the distribution itself is not the Gaussian distribution. Ensemble mean and ensemble median is the same, not the same. And third case, it's a neutral case. That stuff from 2012, yeah, neutral case, okay. If you see the neutral case, if you see CFS version 2, compare with the ensembles, the median and the mean, it's pretty close to the zero. Yeah, sure that this is a neutral case, for the 9 months, but the CFS version 2 still showed the like the El Nino, the increased anomaly to the certain level. Yeah. So this is a 3 special case. Then the plot of the La Nina, El Nino neutral case, the Nino 3.4 domain, the SST, the difference, mean difference, not bias. Okay, only one case you cannot see the bias. Okay, just the mean difference. In general, you can see this is a week. Coordinate of the horizontal is a week, out to 35, 40, the 37 weeks, I think is 9 months. Yeah. So for the summertime, we start from June 1st. For sometimes the model tend to the cold side, okay, and later to the winter time, the earlier or later, the models showed a little bit of warm bias, okay. If we average for these 3 cases, okay, you will see clearly models have a systematic the difference or bias, is a maximum reach to the negative, the half degree, and the positive is about the 0.3 or 4. Is the cold bias around the summer times and the winter time is slight warm bias. Okay, this from this particular 3 case, we are against the using the reference OSTIA, yeah. And give you the quick or short summary of the ENSO prediction. The UFS coupled the GEFS has demonstrated the capability of the ENSO prediction, which could be the preliminary the UFS seasonal forecasting system. Based on 3 special cases, El Nino, La Nino, and the neutral, initialized on the June 1st. Without bias correction, the preliminary the UFS SFS showed even and or better performance than current operational seasonal prediction, CFS version 2, okay. Like other seasonal prediction system, there are systematic error around the tropical and the Nino 3.4 regions. By the way, I can tell you that we also have a 4 evaluation around the other area. Okay, I'm only showing you about the tropical and Nino 3.4 region. Consistently, it shows the cold bias for summer and warm bias for winter. Yeah, particularly is kind of challenging to us. Okay. The ensemble spread of Nino 3.4 SST is much over than the IMS errors. It's larger than other seasonal forecast system. I'm looking at the CFS version 2, you already saw them, and also GFD, the SPIR, and the ECMWF, the 6.5. There, the spread is much smaller than us. Okay. We are using the SPPT to simulate the subscale the uncertainties, okay, and we are ensemble spread is much improved and better for the weather and the subseasonal. And if you look at the largest scales like the 500 geopotential highs for the seasonal time scale, still reasonable. SST globally also reasonable. Only the tropical and the Nino 3.4 domains. We still discuss this kind of situation with the expertise in the community to try to understand, to make the future testing or adjustment. Yeah. Meanwhile, we continue to work on the diagnostic of current experiments, and if possible, we have the resource. I can tell you, we only have a very limited, almost no resource. Okay, at this moment, we plan to run some testing to initialize the model from a different time to see the model behavior, and also the P8 is more advanced model physics and others. We try to run in the P8 based seasonal prediction to look at what it look like. Yeah, I will stop over here. I am already talking about more than 15 minutes. Thank you very much.
Thanks, Eugene. There are a couple of questions in the document here, and I know you can't see them. So you're showing your screen there, but if you allow me just to read them here. Someone, I think it might be Ben Green, asks, on slide 13, you showed biases relative to ERA 5 over the Himalayas that were essentially unchanged between weeks 3 and 4. You attributed this to initialization, presumably the very high terrain. Were you able to look at biases verified against the native reanalysis to see if the week 1 errors were smaller?
What is the question?
But were you able to look at the biases verified against the native reanalyses to see if the week 1 errors were smaller?
No.
Okay.
Yeah.
There's another question here. by, I believe it's Matt Rosencrantz. Interesting that the biases are similar pattern and magnitude. And this is on the second to your last slide of, I think, the first presentation part. Interesting that the biases are similar pattern and magnitude at each lead time. Do you have any thoughts on the implications of that?
This one?
Matt's typing in, not the Nino, the first presentation. Yeah. So the first part presentation. So back, try slide 25 there. Is this?
Yeah.
Yeah, so this slide here. So Matt comments that the biases are similar in pattern and magnitude at each lead time. So do you have any thoughts on the implications of this?
That's very, very challenging. You know, the SST do not. You will see the SST is increasing. Only the downward short wave radiation, you are more consistent based on the eyeball view of the plot. And latent heat, the slight difference increase. Yeah, I think that downward short radiation, the warm bias itself, that could be the heat in that area, the corresponding to the increased warm bias of the SST. It makes sense to me. Of course, that's a lot of the interactions to each other. You cannot see the chicken and the eggs, you know, who is come to first, right? Yeah.
Okay. There's one more question, I believe, also by Matt here, and I believe this is on the ENSO part on your second presentation there. It says, are there any plans to dial back to 32-bit to allow for more computational capacity and get more members and samples?
That's pretty easy. If the variables and you know, of course, we try to 32 bits, you know, to save the resource and running more case and more members. That's good. I hope to. Yeah.
Okay. I don't see any other questions in the forum here right now. So if that's it, I would like to thank you, Jin, for the presentation today, and very much appreciated. And if anybody else has any other questions, they can actually type them into the document, and we can always get that to you, Jin, and get some answers offline here as well. So anyway, we will have a couple presentations next month, I believe. And check out the website, and you can get updated on that. And so thank you everyone for attending, and hope to see you next month.
Thank you, Mark.